Something is quietly happening inside one of the most powerful industries on the planet, and most people haven't noticed yet. Not because it's hidden, but because when you're watching a giant fall, it happens slowly at first, and then all at once. Intel built the modern world. Not metaphorically, literally. The chips inside your laptop, your server, your hospital, your bank, for decades, they carried Intel inside. That wasn't just a slogan. It was the truth. Intel was the backbone of everything digital, the company that made the impossible possible, again and again, for half a century. And now, it's fighting for its life. But here's where the story gets interesting. Because Intel isn't just trying to survive, it's making a move. A massive, unexpected, almost unbelievable move. And the name attached to that move? Elon Musk. Think about that for a second. The world's most valuable AI chip company isn't Nvidia right now in this conversation. The company being approached isn't AMD, it's Intel. The one everyone counted out quietly, positioning itself inside the most ambitious technology empire ever assembled. Tesla, XAI, SpaceX, Optimus, all of it. So the real question isn't whether Intel is desperate. The question is whether this is the smartest move anyone in Silicon Valley has made in a decade, or the last desperate gasp of a drowning giant. Let's go back to the beginning, because to understand where Intel is today, you have to understand what happened to the ground beneath it. 5 years ago, the semiconductor world had an order to it. Intel made CPUs, Nvidia made GPUs for gaming. AMD was a distant competitor. And the idea that artificial intelligence would rewrite the entire power structure of the industry, most people weren't taking that seriously yet. Then something shifted. Not gradually. Like a fault line that had been building pressure for years, it snapped. And the shockwave changed everything. Nvidia's data center revenue went from around $15 billion in 2023 to over $100 billion. That's not growth. That's a completely different category of performance. That's a company doubling, tripling, quadrupling, and then going further, in a single business segment, in just 2 years. Now sit with that number, $100 billion, from one division of one company. In the time it takes most corporations to plan a quarterly earnings call, Nvidia rewrote the economic map of the entire technology industry. And where did that leave Intel? Intel's total annual revenue right now sits around $53 billion. That means Nvidia's AI chip division alone generates nearly twice what Intel earns as an entire company. Every product line, every geography, every customer, all of it combined. And Nvidia's GPU segment still dwarfs it. That's not a gap. That's a canyon. But wait, because the Nvidia story is only half the pressure Intel is feeling. The other half is coming from a different direction entirely. And this one is more personal, more structural, and in many ways, more dangerous. AMD, the company Intel used to dismiss, the scrappy underdog that spent years being ignored in server rooms across the world. Back in 2017, AMD held roughly 2% of the server CPU market. 2%. It was barely a rounding error. Intel owned everything else. Fast forward to today. AMD now controls 25 to 30% of that same market. And here's why that number should make every Intel investor feel cold. Every single percentage point lost in server CPUs represents somewhere between $400 and $500 million in annual revenue. Not once, every year, permanently. So do the math. 25 percentage points at $500 million each. That's not a setback. That's a structural wound that bleeds every single quarter without stopping. But the deepest cut of all? It's not a competitor. It's Intel's own ambition. When Intel launched its IDM2 strategy, the plan to open its factories to outside chip customers, it was supposed to be the comeback story. Intel as a manufacturer for the world. Intel as the alternative to TSMC. Intel as the company that could do it all, design and build, under one roof. It sounded visionary. It still might be. But right now, the numbers tell a different story. Intel's foundry business, the division that was supposed to anchor the entire comeback, reported operating losses of around $7 billion. $7 billion. From a division that was meant to generate income, not consume it. And when you understand why those losses are happening, the situation becomes even more uncomfortable to look at. A modern semiconductor fab doesn't just cost money to build, it costs money to breathe. 25 to 30 billion dollars per facility just to get started. Then depreciation kicks in at 4 to 6 billion per year, every year, whether the factory is full or not. And that's the problem. The factories aren't full. Here's something most people outside the industry don't realize. A semiconductor fab only makes economic sense when it's running at over 85% capacity. That's not a preference. That's survival math. When utilization drops below that threshold, the fixed costs don't shrink. The machines don't get cheaper. The clean rooms don't stop needing maintenance. The losses just accumulate faster and faster. A fab running at 60 or 70% capacity can burn $15 to $20 million a day. Not in development costs, not in R&D, just in the gap between what it costs to operate and what it earns from production. So the core problem Intel faces isn't really about chip design. It isn't even purely about technology. It's about volume. It needs customers, big ones, consistent ones. Customers that don't place orders in the millions of units, but in the tens of billions. And here's where the story pivots. Completely. Because there is exactly one company on Earth right now whose ambitions are so large, whose production targets are so enormous, whose need for silicon is so relentless that it could single-handedly change Intel's utilization math. That company is Tesla. Now, before you dismiss that idea, before you say Tesla is a car company, not a chip company, slow down for just a moment. Because the moment you look at Tesla's actual chip consumption, the numbers stop being about cars entirely. A single Tesla vehicle uses somewhere between 1,600 and 3,000 chips. Not one chip, not 10, thousands. Across every system, the drive hardware, the sensors, the full self-driving computer, the battery management, the displays, the connectivity. Silicon is embedded in every layer of that machine. Now take Tesla's long-term production ambitions. 20 million vehicles per year. That's not a fantasy number from a press release. That's the stated internal target. And at 20 million vehicles, each consuming thousands of chips, you're talking about 40 to 60 billion chips per year from cars alone. But that's just the beginning. Because Tesla isn't just a car company anymore. And that's where this story goes somewhere completely different. Optimus, the humanoid robot, the project that most people still treat as a science experiment. Let's take it seriously for a moment and just follow the logic. A humanoid robot isn't a simple device. It's a real-time processing system that has to handle vision, balance, touch, spatial awareness, and movement all simultaneously. That demands multiple AI processors per unit, dozens of sensor modules, control chips at every joint and every decision point. Conservative estimates put the chip count per robot at somewhere between 3 and 5 advanced processors, plus hundreds of supporting components. Now, Elon Musk has talked about robot production scaling not just to millions, but potentially to hundreds of millions of units over time. Even if you discount that vision by 90%, even if you say it only gets 1/10 of the way there, you're still talking about demand that reshapes the semiconductor industry. At 1 billion robots, 3 to 5 AI chips each. That's 3 to 5 billion advanced chips from a single product line, from a single company. And suddenly, Intel's empty fabs don't look like a liability anymore. They look like the most valuable underutilized asset in the technology world. This is the logic underneath the Terafab partnership. This is why it isn't just a business deal. It might be the most strategically significant manufacturing alliance of the decade. But here's the twist that most coverage of this story completely misses. This partnership isn't just about Intel needing customers. It's about Tesla needing something too, something that most people assume Tesla already has. And that assumption is wrong. Chip design and chip manufacturing are not the same skill. Not even close. Tesla is genuinely exceptional at design. The full self-driving chip is optimized for inference at a level that many engineers openly respect. XAI is building systems specifically tuned for real-world deployment, not brute force data center performance. Tesla knows exactly what it wants silicon to do. But knowing what you want to build and actually building it at industrial scale, those are separated by decades of painful, expensive, brutal learning. Here's what that learning looks like in practice. A modern advanced semiconductor fab costs $10 to $20 billion per facility. To get below 5 nanometers, you need EUV lithography machines. Each one costs hundreds of millions of dollars. The next generation systems high NA EUV are approaching $350 to $380 million per unit. And a single fab needs dozens of them, all working in precise coordination across thousands of ultra-precise process steps. That alone makes it almost impossible for a new entrant to build from scratch. But it's not even the hardest part. The hardest part is time. Building a fab doesn't take months. It takes 3 to 5 years just to reach operational status. And even after that, you're still fighting the yield problem. In early production of a new node, yield rates can fall below 50%. That means half of everything produced is waste, not slightly defective, completely unusable, and that wasted silicon isn't free. You paid for the raw materials, the energy, the machine time, the labor, all of it, for a chip you can't sell. For Tesla, running its own fab at low yield rates could effectively double the cost of every functional chip for years, turning what should be a competitive advantage into a financial disaster. Intel has already been through that. Intel has already paid that tuition. 50 years of manufacturing knowledge, yield optimization, defect reduction, process calibration. That's not something you download. That's not something you hire. That's something you survive. And Intel has survived it repeatedly at a scale that almost no other company on the planet has matched. So when Intel brings advanced packaging technologies, Foveros, three-dimensional stacking, chiplet architectures to this partnership, it isn't just offering manufacturing capacity, it's offering a shortcut through a decade of expensive mistakes. It's offering Tesla the ability to scale silicon without having to learn every painful lesson from scratch. That's the real value of this deal. Not just factories, not just fab utilization, institutional knowledge, manufacturing intelligence accumulated over half a century. But even that isn't the final layer of this story, because there's a scale question that nobody is asking loudly enough. Can the current semiconductor ecosystem actually handle what's coming? Think about what the next decade of AI deployment actually requires. Not inside data centers, not inside server rooms, out in the world, in cars, in robots, in edge devices, in systems that run on batteries, that move through environments, that can't be plugged into a wall and can't afford to consume kilowatts of power just to make a decision. Nvidia dominates AI today. That's not in question. But Nvidia's chips are optimized for a specific environment. High power, high performance, data center scale, stationary, cooled by industrial systems. Those chips are extraordinary for what they do, but they are not designed to sit inside a robot walking through a warehouse on a single battery charge. They are not designed to run inside a vehicle that needs to process the world in real time without draining the entire battery in minutes. The AI deployment challenge of the next decade isn't about raw power. It's about efficiency, cost, volume, availability, and Intel, positioned correctly, with the right customers, running at the right utilization rates, can compete on exactly those terms. Not by building the smartest chip in the room, by building enough of the right chip, reliably, at a price that makes deployment at billions of units economically possible. This is the strategic repositioning underneath everything Intel is doing. It's not trying to out Nvidia. That race is already decided. It's trying to become the manufacturing infrastructure for the next phase of AI, the phase where intelligence leaves the data center and moves into the physical world. And if that transition happens the way the trajectory suggests it will, the company that controls the manufacturing capacity for that transition controls something far more valuable than any single chip design. Now, there's one more dimension to this story, one that sounds like speculation when you first hear it. But when you actually run the logic carefully, it stops sounding like speculation entirely. What if the end game here isn't just about chips on Earth? Energy is the binding constraint of modern AI. Not compute, not talent, not software. Energy. 30 to 50% of what it costs to run a large-scale data center goes to electricity and cooling, not computation, keeping the machines from melting. As AI models grow larger, as inference demands increase, as more of the world's systems run on AI continuously, that energy problem doesn't improve, it compounds. The cooling requirements don't shrink, they expand. And on Earth, there are hard physical limits to how efficiently you can solve that problem. Now, look at what's happening with SpaceX. Starship, the rocket system being developed to reduce launch costs to somewhere around $100 to $200 per kilogram. Compare that to where we were a decade ago. $20,000 per kilogram to reach orbit. That's not a 10% improvement. That's not even a 50% improvement. That's 100 times cheaper. At $100 per kilogram, launching hardware into orbit starts to look less like a government program and more like a capital investment decision. Similar to building a highway or a power grid, solar panels in space receive sunlight without atmospheric interference. No clouds, no night, no seasonal variation. Roughly 30% more energy per panel than the same system on the ground, operating nearly continuously. Cooling, the budget item that consumes nearly half of data center operating costs, works completely differently in a vacuum. Heat dissipates through radiation. No fans, no liquid cooling loops, no chillers, no mechanical systems, no energy spent on thermal management. The environment itself is the cooling system. Combine those two factors. More energy in, near zero cost for heat removal. The operating economics of a space-based computing node start to look genuinely competitive with terrestrial data centers, not in the distant future, on the trajectory being built right now. And here's where Intel re-enters the equation, one final time. Even if space-based computing becomes viable, even if the economics work out the way the trajectory suggests, none of it happens without hardware. Chips that can survive radiation exposure, chips optimized for efficiency, not just performance. Chips built in volume, reliably, at a cost that makes deployment across orbital infrastructure economically rational. That's not an Nvidia problem. Nvidia's chips are designed for a different environment entirely. And underneath all of that, the bigger question, the one that this entire story is really asking. When the age of physical AI arrives, when billions of robots walk through the world, when millions of autonomous vehicles navigate without drivers, when computing moves off the planet entirely, who will actually build the brains? Will it be the company that designed the smartest chip? Or will it be the company that figured out how to build enough chips, reliably, at a scale the world has never seen before? Because in the end, intelligence without infrastructure is just potential, and potential without execution is just a very expensive idea. Is Intel too late to matter again? Or is it standing at exactly the right factory, at exactly the right moment, waiting for the largest wave of demand in the history of silicon to arrive?